Well, hello everyone. Good morning, good evening, good afternoon, depending on which part of the world you're watching us from, live or later. We are so happy to have you here again. For those of you who know me, I'm Mudit. I'm one of the founding members of AI Planet, and we are a global data science community. Before I go any further, I would want to quickly go out there and check if you're live across platforms. So please give me a minute. We have Parinita, who is the guest speaker for us today with us on the backstage. But before we dive into the session, I just need to check that there's no one getting missed out because this session is going to be quite an exciting one. Um, Let me just check. If you can hear me, you can also put it in the comments. At times, there may be a slight lag for me to receive your comments, but I am quickly checking it out. Just give me a second. Your comment? Yeah. Cool. We are live across platforms. Great. Thank you so much, everyone, for joining right now, who are joining live. And I welcome everyone who is joining later also. As shared, I'm Mudit. I'm one of the founding members of AI Planet. And we are a global ecosystem. Our vision is to educate and build AI for all to solve some of the meaningful problems out there. We started around 2 years ago with a free boot camp, and over the due course of time, we have been able to impact more than 100,000 learners and build a community of over 100,000 plus learners from 150 plus countries. So, if you are into data science, data engineering, or something in and around that, you can absolutely feel free to visit aipanel.com, explore the resources that we have there. Most of them, I mean all of them, are open source. You can learn them for free. So without any further ado, let me give a quick introduction of what we are going to discuss today. So we'll be talking about the title, as it says, is steps of an AI product lifecycle. Now, while it's quite self-explanatory, to give you a brief intro, we'll be talking about various steps on the, I mean, because of the breadth of the entire scope of topic, we wouldn't be diving too much onto implementation side of things in this particular session, but we will try to give you a proper holistic overview so that when you end this session, you have a proper understanding of, an overview of what happens when it comes to building products which are around AI. We'll be talking about problem scoping, data identification, data processing, pre-processing, model training, deployment, and improvement. And this session will be taken by Parinita, who is currently working as an AI product manager at IO GmbH, which is as the name says, it's a German company. She's a hardcore digital native. As she describes herself in her bio, she's somebody who would get lost if she's not using Google Maps, and she's an absolute AI enthusiast. She has been working in the industry for around 7 years now. Comes with a computer science background, so technically, while we can answer a lot of questions that you might have, we will try to stick to the agenda. This being said, if you have any questions, please feel absolutely free to put them across in the comment section. We will be happy to curate them and ask them. So let me quickly invite Parinita also on the show. Hi, Parinita. Thank you so much for being with us today. You're live.
Hello. Thank you, Madad. So quick confirmation I need from your end. You're able to see my screen, right? Right now.
Yes,
Um,
I can see it. I mean, the audience cannot. I mean, we can put it up for them in a minute.
yeah,
But yeah, okay. Yeah,
cool.
yeah, it's visible. But yes.
Thank you so much for confirmation. Yeah, thank you so much for kind information as well, kind introduction as well. Hello, everyone. Like Mudit informed, I'm Parinita, and I currently work as an AI product manager. And the reason why I chose this topic today is because during my tenure as a product manager at IO, the company I work for currently, I realized the steps involved in the AI product cycle are kind of different as opposed to the traditional software product cycle. Um, I think the reason because there are so many unknowns and uncertainties and challenges that come along with implementing an AI product. So that's one of the reasons why I chose to go with this topic today. Hopefully, you'll all get information, productive information out of the session. So yeah, without further ado, let's start.
Yeah, over to you. I'll go to the backstage. Yeah.
Yeah, thank you. Cool. Um, so fine. So like I mentioned, so today I wanted to talk about a few steps of the AI product cycle. So before starting any effort, AI effort, we need to understand what are we trying to do, like what problems are we trying to solve. Are we even trying to solve the right thing? What if you're trying to do something which is, to begin with, not a problem by itself? It becomes super important for you to identify the right kind of opportunity, or the right problem that you're trying to solve. And that's exactly where several techniques come into picture. Like, for example, user interviews or customer interviews. You're just trying to talk with either random people or potential customers of your product that you're aiming to build, and then just asking them about certain user experiences, or their experience using a product. What kind of pain points are they facing right now? And just trying to talk to them for informally, and trying to capture those pain points in itself can provide so much of information to you, give you an opportunity to start coming up with ideation process. And then there are user personas. Like, you can, through these interviews, through these communications with customers or potential users of your product, you build personas and start associating the empathies and the emotions that they have with certain product. um, and also some other techniques that you can use to understand what kind of problems you can resolve is really doing competitive research analysis. And most commonly, most commonly is the brainstorming and the research techniques, where you sit with probably set of potential stakeholders, or your team, your product team, or just the cross-functional members, just sit together and try to uh, discuss a few things, and discuss some pain points, some challenges that you're facing in a current product, or a component, or a solution, uh, or process, etc. So these kind of techniques are what are called discovery techniques. So basically, like the name says, you're trying to discover things, and you're trying to analyze what right thing can you build at this point. And then next we have things. Once you know once you have identified the right opportunity, then you have these steps, like, for example, implementation. And then you have, especially for the AI, you have uh, like anything and everything starts with data, right? Because AI models are so data hungry. So yeah, data collection, metric definitions, deployment. So all of these are the next steps that follow after your discovering work is done, which is basically fixing all the pieces of the puzzles together. So this is where you can call these things our delivery techniques. And now I want to talk about this phase where discovery and delivery become so tightly coupled, especially for an AI project, because an AI project, number one, is um, kind of emerging technology, considering different, like the spectrum of domains. And so each and every step within an AI development cycle comes with so many unknowns and uncertainties. So it to us looks like a tightly coupled loop, where there's discovery. You're trying to understand how to do the right thing, build the right thing. And then there's delivery, where you're trying to understand how to build the things right. And I will be talking about specific steps in this loop, like problem solving and data identification, competitive research, which all fall into the discovery part. And then we have processing, the ML model trainings, model deployment, etc., which fall into the delivery part and are closely looped together. So I will be taking you all through a real-time example that we've done in the current company I work for. Um, and yeah, so let's go. Starting with problem scoping. So I would like to take an example of one of the current products, like even before I continue. I work, like Mudit mentioned, I work for a company called IO, which is a German company, and we are specialized in the ad filtering domain. If you're browsing the internet and if you come across um, super annoying ads, like super obstructive, privacy intrusive ads, then and if you decide to go for a ad blocker to experience better user browsing experience, then chances are 90% you've come across our products, which is like AdBlock Plus and AdBlock. And today I will be taking an example of how we identified a pain point with the existing um, implementation and existing state of AdBlock Plus, and how we want to optimize this using AI. And the first step, problem scoping. So if you look at the screen, and this is basically how your screen looks with ads, and the screen without ads, like similar for the phone, for the mobile. You have a screen with lots of ads, and then the screen without ads. And we cannot deny that the ads do definitely annoy us to some extent, and we just wish most of the times that we don't have ads and try to get information and get things done that we are actually aiming to do um, on the internet. So AdBlock Plus is one of our products which exactly tries to do that. It tries to filter off the ads, annoying and privacy intrusive ads from the website that you're browsing, and it's basically a browser extension. And the way it works is, when you request for a website as a client, um, if you have the ABP installed on your browser, then the ABP first takes this request coming from the client and looks into the filter lists and tries to. So filter list is a set of rules that tells us if a given domain or a given web page has ads or no ads, and then um, uh, um, uh, um, tells us what needs to be filtered versus what doesn't have to be filtered. So ABP uses this logic called filter list, and it by looking into the filter list, it either allows certain ads which are not super annoying, or it either blocks the ads which are super annoying. And then as a result, what happens is you're seeing a website with less ads which are not super intrusive and abductive. So the main engine here is the filter list. So these filter lists is what is allowing the AdBlock Plus to identify what's an ad versus what's not an ad, and what to block and filter versus what to not block and filter. And when we talk about filter lists, there are so many things that we cannot help but ignore. The thing is, if there's any breakage or anything, any disruption in the filter rules, then the ABP is not functioning as per desired or as per intended. And that sort of makes filter list a single point of failure. Um, and also the fact that these filter lists are super huge. Um, like for example, let's talk about the very popular filter list like EasyList. And this EasyList itself has like 60,000, 70,000 lines of code. And imagine these filter lists need to be regularly reviewed and updated by filter list authors or filter developers, etc. So that's too manual and it sounds super hectic. And so we sort of identified these pain points and identified an opportunity here, thinking that okay, this could be the place where we can come up with ML automation solution which can automatically detect ad and filter the ads, and that's how we did the discovery here. So once we now, like I mentioned, problem scoping, we identified the problem, and we now know what can be tried out. So the next step was to know what kind of data needs to be collected for this. So if we just think about any data in the wild, it's like a huge web is pretty huge, and you kind of get all kind of data, but uh, trying to identify the right kind of data that can help you with solving the problem is pretty difficult. And here again, we tied our process back to discovery, where we started to brainstorm and research what kind of data should we start gathering. We know we definitely need ads data, and we know we need web data, but how and what kind of process can we use to collect this data? So we first, based on the other researchers out there, we first started trying this method out, which is called perception-based ad detection, where we started taking the screenshots of the random web page and started identifying the ads by image processing. For example, if you see here, we try to identify a given post in the web page, a given section as an ad or a no ad based on certain elements like the ad choices, the presence of these elements, or the presence of certain elements on certain sections of the web page, etc. Um, but this seemed to be super process heavy and computation heavy. And the fact that we are a browser extension, it is super important for us to be lightweight. And so we continued our research. We continued our ways of researching about collecting data, and then we realized that we should probably just go with something straightforward like the web page itself, because the web page contains all the tags in it, which in itself can give us the kind of data that we would want for the model to later identify a content as an ad or a no ad. So that was our initial thought process, like, okay, let's just capture a web page and go from it. So when you look into a web page, so it's basically like when you look at the DOM, this is pretty much how it's structured. Like there's tag and there's like tags within, and it's structured. But there are certain challenges. It's super unbalanced. It's wild data. It's super raw. And we tried looking into the distribution of data in this, and distribution of tags in this, and we were not able to get a proper insights in this case. Like for example, um, uh, as you can see, the distribution of tags in the entire data set that we sort of collected. In a few minutes, I'll talk about the amount of data that we tried collecting. But so when we looked into the entire data set, this was how the distribution looked. And then the distribution for ad nodes looked this way, and distribution of tags for the non-ads looked like it kind of looked similar, and we weren't able to gather very much insights from this raw data. And yeah, we did collect around 200 million data points, and how I'll discuss in a few minutes. So the data was super unbalanced and not really making too much sense. So what we tried doing is we wanted to get some so while continuing the discovery process, what we tried doing is we came across this idea of using the existing tool that we have, existing solution that we have. Like for example, our ABP already identifies the ads using filterless. Like the ad filtering technology is out there, which identifies a given ad, a given content on a web page as an organic versus an ad. So how about we leverage this technology and try to gather the ground truth data, which we can use for training our models, right? So what we did is we forked the ABP, the AdBlock Plus that we have, and we tweaked the technology tweaked the functionality of ABP in such a way that instead of filtering the ads here and displaying non-acceptable free, non-acceptable ads free display, what we try to do is we tweaked it in a way we wanted to not filter the content coming from the AdBlock Plus, rather annotate it into ad versus organic. So that's how we implement it. So basically, the data coming out of the ABP fork that we created doesn't really filter the ads, but it labels the content versus labels the content as content versus an ad. And then we thought we can use this data as a ground truth data to tell the model what is ad versus what is not an ad. And so that's how we went about uh, identifying what kind of ground truth data we would want here. So the challenge here was really, okay, we now have a ABP fork and we can get the data that we are aiming for, but machine learning efforts, machine learning models need data in really huge amount. And how do we scale up this data collection process? And for that, we tried implementing this ABP fork with the headless Chrome and Puppeteer, and came up with an in-house web crawler, which automatically goes through some of the websites and collects all the kind of data that we aim for, which is like a set of labeled content as an ad versus no ad. It was not a very sophisticated web crawler per se, but it was serving the purpose for us. And the purpose here was to get data in scale so that we can train our models the right way. So yeah, that's how we went about collecting the data that we needed. Now, the next step was for us to process this data. We do have the web data, but we couldn't have fed this as is. We wanted to convert this into adjacency matrix and feature matrix in order to feed the algorithms which later we chose to train the model with. So as you can see here, we have a HTML page, like a very small example. And then what we did is we took this, converted into a DOM and then into a adjacency matrix. There's, for example, here there's div. There's and div contains two tags, the H1 and the P. And so the div is a tag, and it has H1 and the P as child nodes. And when you turn this into an adjacency matrix, you can see here, like for example, there's the links represented in zeros and ones. For example, if so div doesn't have anything else linked to it, so it's basically 0, and then H1 is linked to div, yes, and so that's 1, and then a P tag is linked to div, so that's a 1 again. Similarly, the H is linked to div, so 1, and it's not linked to itself, and 0 0. So that's how we created a adjacency matrix out of this. And then there was also feature matrix, in the sense we selected a few attributes from these web pages as features. We started with flagging, identifying node ID, parent ID, node level, stack types, etc. as the features, because they have certain information associated with them when it comes to content. So again, this is all research going on, and we started with this, and we then had our feature matrix ready and the adjacency matrix, and now we wanted to try out training, selecting the certain machine learning models, algorithms that can perform the classification for us, which is ad versus no ad. Going to the model training part, we tried different approaches, and we tried different ML algorithms, and we tried different techniques. Like for example, we tried graph neural networks based ML models. We tried combination of ML models and tree based, and then we tried supervised versus self-supervised learning, and then graph versus node classification. I'll talk about these things a bit into detail. Now, so going back, we have the data, we have pre-processed it to an extent, and now the next steps is for us to feed this to the model and hope for the classification to happen. So this is the state we are at, and the very first approach is with a graph neural network. So we have the data, we have the node features and the adjacency metrics. We feed this information to the graph neural network. And now graph neural network, through its message passing mechanism, generates node embeddings and performs the classification on node embeddings. Which results in given content as an ad or a no ad. I'm being at very high level. So quickly to tell you what a graph neural network does. So graph neural network is one of the popular deep learning algorithms where you have several layers, especially the input, then the processing layers, and then the output layer. So input layer is where you're giving the data, and these layers is where the processing is happening, and the information, this data is being processed, and then the output of this is really an content of your data being classified as an ad versus no ad. So what exactly is happening inside of this graph neural networks? Like previously I mentioned, the graph neural networks has the data, the features that we have selected to start with are the node ID, the tag type, parent ID, etc. So the data that you're sending in, like a tag, a node in a graph contains all of this information about itself, and then it also has information about adjacent nodes. Like for example, H1. H1 contains node ID, tag type, parent ID, etc. So there is a message passing mechanism where the H1, the information about these adjacent nodes is being sent to each other, and now there's a diff node which contains information about not only its features but also its adjacent nodes, and that's how like the node embeddings are out there, which contains the information about the adjacent nodes as well, which allows which gives more information about the node in a graph. So that's pretty straightforward. Like I mentioned, we use the graph neural network for the first approach, where we are just feeding this information to the graph neural networks out of the shelf, and then try expecting the data to be an ad versus no ad. So the second approach we had is an hybrid approach, where we try to use graph neural networks along with a classic classifiers like SVM or random forest, logistic regressions, etc. So what we did here is we took the graph, the node features and the adjacency matrix, like fed this data to the graph neural network, and the graph neural network, instead of the graph neural networks performing the classification on the node embeddings that are generated, we are using these we are feeding these node embeddings generated by graph neural networks to the classical traditional classifiers such as logistic regression, random forest, and in turn, these these classifiers are the one that are performing the node classification, which results into the outcome of data as an add versus no add. So that's something that's the hybrid approach that we took. And then next we tried classic tree-based models where we took the data as is and just fed the node features to the tree algorithms, and the node classification is performed, resulting in content as an add or a no add. So these were a few methods that we tried, and when we evaluated these models with more and more data, like the amount of data that we used is, for example, um, thousands and thousands of web pages data coming from different sources like CNN, Amazon, Bloomberg.com, etc. Then search engine web pages, search engine result pages, um, bot data, etc. So when we used and trade and performed benchmarking on these models with this kind of diverse data, we had our numbers looking like this. We had the random forest classifiers on node embeddings, which is the hybrid approach I spoke about, had a pretty good accuracy, and the only tree based approaches had a good accuracy as well. But what really was a surprise for us during this was really that the GNN classification, the first approach that we used, where we fed the data directly to the graph neural networks, didn't result in good numbers. Um, so this was opposite of our understanding. Like we weren't sure what exactly is happening. Um, but yeah, so this is how our numbers look like at the preliminary state. Um, but there's a lot of retraining and reevaluation that definitely is required here. But with this kind of numbers, we try to um, move into the next stage, which is think about deployment, and see how that works, because there are a lot of unknowns here as well. Like for example, ABP is the native language is the JavaScript, and all of this that we've been trying and experimenting is in Python. And so the model implementation itself is a challenge. Like at the end of the day, when we are talking about deployment, we'll have to convert all of this implementation that we've been doing in Python into native code base, like native language compatible, which is JavaScript. Um, and that's a challenging aspect. And then the model latencies, like I spoke previously, we are a browser extension, and it becomes absolutely important for us to be lightweight and quick and not have latencies. So making sure that we don't have latencies in binary sizes, again connecting to the fact that we don't want to be heavyweight. Trying to optimize the binary sizes or the model file sizes is absolutely important for us. So these are some of the challenges that we had with deploying the model. We used certain out of the out of the shelf libraries, like for graph models, we use TensorFlow to convert the DOM to model ready features, and for tree-based models, we used M2CGen, the existing library out there for this kind of conversions. And so far, for no, and also the fact that we have all of this implementation right now in the background. The background script, like for example, when we talk about extension, browser extension, we have mainly four different kinds of files, like manifest, the background script, the content script, so when we all this model implementation right now is done in the background script, because each and every time uh, we initially tried experimenting by placing this implementation into content script, and each and every time the page loaded, a web page loaded, the model had to restart and infer, and that was too computational heavy. And so we tried experimenting by placing this model implementation into the background script, where uh, uh, the model had to like load once and run multiple inferences, and this kind of reduced uh, or made the whole process a bit optimized compared to what we had otherwise by placing the implementation in the content script. So with this, currently we have an inference speed of around zero point 0.3 milliseconds, uh, but that's really too much, considering we have thousands and thousands nodes in a given web page, and zero point 0.3 milliseconds as an inference speed is still not very sufficient. But we are there with this. So we definitely have a lot of um, things that we want to do as part of our improvement strategy. And so again, tying back to the discovery process that I started with, like we definitely want to optimize our data collection process. We want to optimize the quality of data that we are collecting, and try more and more um, algorithms. We are now trying the graph neural networks and the proper classifiers, but we definitely want to try different other techniques, such as natural language processing, etc. And and pipeline automation, like really having this end-to-end pipeline established, so that this whole process is more efficient. These are some of the improvement strategies that we have. Um, um, so so this again ties back to the fact that we are, though we've done these things, it's all uh, going back and forth between the discovery and delivery, because each and every point of time we do something, we need to again do research and try to find out more answers that comes along our way, like the unknowns that we come across. Um, so yeah, that's kind of what we have done so far. But this is again the experimentation, and we are at a very preliminary state. But eventually, like I mentioned, as a part of improvement strategy, we want to be there, where we ultimately do not want to. We don't have to need filterless completely, but do this whole process of ad detection. Uh, using automated using AI/ML. We have documented this whole process in technically deep way, and you can access all of this information at a certain depth using this link. And yeah, I think with that, I will probably just um, ask say thank you and ask if you have any questions or anything. Um,
Oops. Sorry. Yes. Okay. I'm glad to be live again. And thank you so much, Parinita, for that insightful session. Um, we have a couple of questions, and we would want to take them up. So, first one that Sam is asking is, in the slide before deployment, you mentioned, I think,
mhm.
various evaluation metrics, I think F1 score and all. And then it's asking, how did you go about deciding to retrain the model? Do you do it always?
Yes. So about retraining, we do always retrain the models, but so we kind of defined ourselves a limit of going above 80% accuracy. So we wanted to um, understand if we are able to have the F1 score above 80%, then uh, 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 we wanted to proceed with try experimenting the deployment efforts. If not, go back into optimizing our data, do more feature engineering, and try to select more features and do more experimentation. Like I said, it's not completely finalized, the kind of data we have, the kind of features we have selected right now. We definitely want to go back and improve our feature engineering, and that's also a gradual iterative process, if you will, right? To always try different features and optimize. So yeah, the moment we notice that our model is performing above 80, which we thought is reasonable, we try to go with the next steps and explore more in the coming phase.
Okay, thanks. But why 80? How did you decide that particular number? Because that is very
Um,
different for product to product, right? There are some products which operate at much lower accuracy or efficiency. So, I mean, yeah.
Yeah, precision becomes one of the important metrics for us. Like we can, as our product is the one which filters the ads, like it's super important for us to um, not filter something which is organic and we don't want our machine learning model to identify something organic as a ad, and so we wanted to have high accuracy at this point, and also not too high. Not We aimed at 80% only because this is a research process, and we're starting something from nowhere. Like we are starting from scratch, and we wanted to try optimizing from here on. But to start with, for this particular use case, 80 seemed to be a reasonable number. If it's better than that, of course, I mean, if we have higher number, it's definitely advantageous. But like I said, if we have low F1 score, then that's kind of risky in the sense we are not then talking about filtering organic content by mistaking it for an ad, which is definitely not called for, if that kind of answered your question.
Yeah, it does. Thanks. And on that note, I was very curious to understand how exactly do you get the. I mean, when we speak to a lot of young founders and all, I mean, upcoming founders,
Mhm.
they usually are a bit confused whether one, if they have enough data, second, how do they get enough data if they don't have it? In the sense, we're not talking about data augmentation and all, but in the sense, how do you even get data? For example, in your use case, where you have to find
Mhm.
whether something is an ad or not. So
Mhm.
how did you go about it in your case? Because you mentioned that you worked with a very large data initially.
Mhm. Mhm.
Yeah.
Yes. Let me take you back to this slide. So here, this is where I can explain a bit more detailed about how we collected the data. So we have the ABP, the AdBlock Plus product, and what we try to do is we try to fork this product and create a fork of this product. And what AdBlock Plus currently uses the filter list, like which is the set of rules. It refers to this filter list and uh, filter out the filter out filters out the ads on the screen. So that's the intended functionality of ABP. But what we did is we we wanted to take this existing ABP, fork it, and implement or tweak this functionality in a way that instead of the ABP filtering out the ads, it labels them. It labels by using the filter list. It knows what are the ads. So instead of filtering them out, it's annotating the data for us. It's saying, okay, this is the ad, and the ad which is not being filtered is by default considered an organic content, versus the one that is uh, otherwise used to be filtered is now the ad. And we used this. um, so that's what is coming out of the ABP, like the forked one, the version that we are now creating to collect the data. So the outcome is really the data with content in a web page labeled as an organic content versus an ad. And this is the data we used. And now to answer the second part of your question, how did we use this kind of data in large scale? We built a in-house web crawler to automate this whole data collection process. Like if we could have asked, like hired like many people to use this uh, uh, customized ABP fork and provide us more data. But instead of that, we chose to use a web crawler, and by using Headless Chrome and Puppeteers and other solutions out there, we built an in-house web crawler. Um, um, and then we started running them on multiple URLs and some random web pages, just to automatically get the data into our server.
Yeah. Okay, got it. Thanks a lot for that answer. There is one question that is asked by two of the community members. So first of all,
Mhm.
so for example, Sabyasachi has asked, how do you plan to experiment with NLP, and are you planning to use any pre-trained models? And as an extension of that, Nilotpal has asked, have you tried using pre-trained models? What's your take on it in terms of ease, etc.?
Uh, so first question, thank you for the questions. The first question, NLP. Um, it is on our radar, it is on our roadmap to start experimenting with NLP, but we still haven't started the efforts in that space. But the idea is to use the existing NLP algorithms out there, and use the similar. Well, we need to figure out how we want to start using, start experimenting with NLP, but I think uh, I think our approach would be to first start with the models which are already functional out there, and then try experimenting customized approaches in and around that. Hopefully, in next few months, so we have experimented this, and I can come with that information here.
Yeah. Okay. So, but that's an interesting take where you say that, okay, you will use pre-trained models for experimentation, see if it is working out for you, and then you will consider making a custom model for your use case, if I'm getting it correctly.
Yes.
Okay.
Because that's kind of how we tried with the graph neural networks as well at this point. We had this graph data in the form of DOM, and then we fed this to an existing graph neural networks and customized in and around this ways of also, adding the traditional classifiers with the graph neural networks, and going about classification of a content as an ad or a no ad. So we might probably experiment on the similar lines with NLP.
Okay. And on that line, let's pick the second question, which is slightly um, kind of answered, but what's your take in terms of ease and all? How do you evaluate whether you should be using a pre-trained model or not? Um, because there are a lot of platforms that offer it, including AI Planet on today's date. So, what do you think about it?
Um, I would actually let the engineers answer this question, because they are ultimately the experts who would have a strong take on this.
Yes.
Uh, but I'm me as from my perspective, I think it's always an advantageous approach to use an existing solution out there as opposed to going from scratch. So, but that's my take. But I would let the engineers answer this question definitely.
Okay, thanks. But I have an interesting question. So you always, I mean, what I mean by always is traditionally you come from a computer science background. You've been a developer and I think a manager also, and then you transition into AI product management. Did you feel any significant difference between the traditional technical product management or product management versus working with AI products beyond what you
Um,
mentioned in terms of failure rate and all?
Yeah, sure. So yeah, I did start my career as a software engineer, and I've been in a couple of roles before I decided to move as a product into product management as a AI product manager. Um, so just before working here, I've been working as an product manager in the enterprise data and consumer engagement space. Um, my focus was more on delivering the solutions as opposed to discovering what can be done using such emerging tech like AI. So, I mean, from my personal experience, in my previous experience, and the solutions were kind of available, and we tried researching a few things, but not so I mean, every development life cycle has comes with a lot of unknowns and uncertainties, but I think the traditional ones seemed much straightforward compared to the AI product cycles, because here in AI, especially like a domain such as ad filtering, it becomes kind of challenging to understand how to tackle a certain use case. There are so many unknowns, and there are so many discovery and research and brainstorming and everything that is required to understand and even to get your approach right, um, as opposed to just going on doing things, which becomes very resource intensive and expensive. So yeah, I think the interesting thing about being a product manager in AI space is really, again, looping these two things, like continuous discovery and continuous delivery, like trying to understand what we are. You'll reach at a point where you'll be like, you'll cross question yourself, okay, are we even doing this thing right? Then you'll have to again go back to discovering things, doing some research, understand how competitors are doing this, if they are doing it, and things like that. So I would say this is more challenging, yet the learning curve is really high, and it's good.
Okay, great. Well, with that, we are towards the end of the session. We have a few comments where people are thanking for the insightful discussion, but I think um, every single person would have um, received a lot of information, in the sense that we're thankful to you because of various reasons. One of them being that you went so much into a particular use case so that people could relate better and could get a more actionable insight from it, I would say. So thanks a lot, Parinita, for preparing this presentation for the community and delivering it on a Saturday evening. Thank you so much.
Thank you, Mudit, and thank you all. I wish you all happy holidays and advance happy new year. Thank you.
Thank you. Bye, everyone. We'll see you again next Saturday. And happy learning, happy weekend. Cheers. Bye.